So we have made it to chapter 6, which is the last unit, the last chapter that we cover in unit 1. It's another one of those big chunk units, and we're going to cover it in 3 parts, much like chapter 4, just because we are going to establish a bunch of specific items dealing with symmetric, approximately symmetric data, just like we looked at skew data with histograms and box plots so we can compare them. We want to look at this normal model and standard deviation as the ruler that we're going to use. So as always, with our homework, please read the chapter and then work on the problems that are assigned. And then right after this, there will be some review, extra credit, multiple choice, and then our test. That will be most likely the 1st of October. So keep in mind as we move on. So the main objective for this chapter, as we cover it, students are going to calculate a z-score and demonstrate the effect of adding to and scaling a data distribution. This whole idea of scaling and shifting a data distribution will come up a handful of times, and it's important to understand the ramifications that we have. Additionally, this whole idea of a z-score comes up over and over and over again when we are trying to standardize comparisons. So let's just jump straight into it. The standard deviation as a unit of measure. So remember, way back at the beginning of the year, I asked you guys to compare shoe sizes for adult men and women. So we know that women tend to have smaller feet, and male and female shoe sizes do not represent the same size foot. So if someone has like a man's size 9, it's not the same as a woman's size 9. But it is possible to compare measurements of a woman's size relative to other women with similar measures for men. One comparing his size with the size of other men? So of course, the answer is yes. I wouldn't have asked it otherwise. So like this idea is, can we compare apples and oranges? And this comes to this idea of a standard deviation. So the unit of measure we can use for comparing differing data values is standard deviation. The standard deviation tells us how the distribution of data values varies, which makes sense, of course, in relation to the mean of the distribution. So we're always using standard deviation to say how far we are away from the mean or the average. So it is ideal for comparing one individual to a group and for comparing groups with differing means. So I have repeatedly said so far in Unit 1 that statistics is the study of variation. The most commonly used measure of variation is the standard deviation, and it forms the basis for nearly all of the statistics we will do this year. So get used to it. Mean standard deviation for approximately symmetric data. And so this idea of the standard deviation comes to a standardized score. If I wanted to compare someone's height of 6'4" for a male versus 5'9" for a woman, and I asked you, how unusual is one of those? How do we standardize those to compare those differing people? So a data value is converted to a standard score to provide means for comparison. We are converting it to this unitless idea so that we can actually compare them. We convert individual data values relative to their own standard deviations using the following formula. Z, which is a z-score, first time we're seeing this, is the observed value minus the expected value divided by standard deviation. Or another way of saying that is the score minus the mean over the standard deviation, or the y minus y bar over the sample standard deviation, so S, or we can use y minus mu, remember that's mu, which is the population average, over sigma, SGMA, and that is the population's standard deviation. The resulting value, denoted as Z, are called, quite obviously, z-scores. So remember, if you are finding a z-score, it will be observed value minus the expected value. Expected also means mean, divided by standard deviation. Put 5 stars around this because we will come back to this again and again and again. So with the standard score, or the z-score, remember, this is to convert a raw score, some measured data value, into a standardized score. The standardized score is something that we compare other things to. Raw scores above the mean will have a z-score that is positive. And a raw score below the mean will have a z-score of a negative value, or less than 0. With standardized values, or z-scores, these do not have units. No units. By standardizing, we're removing the context from the different pieces of data, and then we are able to compare like with like. So z-scores, what they are the distance of an individual data value from the mean in its own standard deviations. In other words, a z-score is the number of standard deviations away from the mean for a data value, which means a negative z-score tells us that the data value is below the mean, whereas a positive z-score tells us that the data value is above the mean. Just to reiterate this, a z-score indicates the number of standard deviations an observation falls from the mean. And we say this, but if we have a mean score of, let's say, 50, and the standard deviation is 5, if we're using this as a ruler, we can go one standard deviation above or one standard deviation below, and we would call that one. That's our unit of measure. So why do we bother doing this? Standardized values have been converted from their original units to standard statistical unit of standard deviations from the mean. This is all of these conversions that we're doing are now, we can say we are X number of units away from the mean. Thus, we can compare values that are measured on different scales, with different units, or from different populations. So now we can compare the shoe sizes for men and women. So the values give us a measure of how a data value compares to other data values of like kind. A measure of how different from an expected value is a given data value. So for instance, way back in 2015, the SAT test had a mean score of 511 for math, with a standard deviation for the math scores of 120. An SAT score of 550 would have a z-score of, well, the setup would be our score, our data value, minus mu over the population standard deviation. Notice these aren't there wasn't a sample of a class that was taken, so these are the population averages, which is why I'm using those symbols. So if we do 550 minus 511 all over 120, we get 0.325. The way we interpret that is that tells us the score of 550 was approximately 1/3 of a standard deviation above the mean. So maybe someone goes and takes the ACT next. Well, how would that score compare to an ACT score of a 23 on the math portion? So if we're trying to figure out what test we're better on, wouldn't it be easy if we can compare one to the other? Well, what do we need? Well, the ACT results from that same year of 2015 had a mean of 20.8 on the ACT with a standard deviation of 5.2. So if we were calculating the z-score for a 23 on the ACT, the z-score, if we remove the units, would be 23, our data value, minus the mean over the standard deviation. 23 minus 20.8 over 5.2, that gives us 0.4231. A z-score of 4.231 tells us that a 23 is about 0.4 standard deviations above the mean ACT score. Thus, if someone was saying who did better, or did you do better on the ACT or the SAT, you could clearly say that a score of a 23 is better than a 550 on the SAT, relative to the mean for each of those tests. So when we put the context back of their scores, we're always comparing to the means of each individual ones. But when we standardize, we are looking at the same mean, which turns out to be 0. So what are we doing here? Let's just go into this a little bit of shifting data and scaling data. Think back to a math class. When we are shifting data or a horizontal translation, if you are adding or subtracting a constant amount to each and every value in the distribution, what you're doing is you're just adding or subtracting the same constant to the mean, the median, and all measures of position. This has the effect of shifting the distribution horizontally. What does not change are the measures of spread. With shifters, the variance, the IQR, the range are not affected by adding a constant to every value. If you have a distribution and then you shift it over X number of units, the distribution is the exact same spread, variance, IQR, but it's just moved. What changes are the mean, median, and other measures of position. So we are going to do this in a little bit. So we're going to open up our graphing calculator just to get it started. And in the United States of America has been half-heartedly trying to implement the metric system of measurements. Last year, students were asked to estimate the length of their classroom in meters. So the following data shows the results from room 110. As you can see, there are 44 data values between my statistics and AP statistics class. One plot shows our guesses, and it was found by subtracting the correct value, which was 13 from each estimate, we could see the guesses compared to their error. And if we look at these two histograms, we can see that the guesses are on the bottom, and we get our majority of our distribution of people guessing right around 13 or 14. And then if we shift the guesses backwards, or subtracting 13, even though the distribution is moved, nothing changes about its looks. By rescaling the data, which is a stretch or a compression, when we divide or multiply all the data values in a distribution by any constant value, all measures of center or position, so the mean, the median, percentiles, Q1, Q2, Q3, and measures of spread, such as range, IQR, standard deviation, are divided or multiplied by the same constant value. So when we are rescaling the data, everything is affected. With shifters, only measures of center are affected. With scalars, everything is affected. So if we're building off of this example from last year, the errors in meters can also be measured in feet. And if you know your unit conversion, 1 meter is equal to 3.28 feet. So now we can multiply each value by 3.28084 and compare the plots and see how accurate we were from meters to feet. So now that I'm showing you these distributions, and we can see that the data got even more spread out and the center is moved further away in both of those distributions, what I want us to do is this exact work. So I'm going to show you on the TI Nspire, but if you want to follow along, I have the same work described of what we can do in the TI-84. So pause the video and type in the data values for each of the guesses. So if we look on my TI Nspire, I have columns named guess, and I have all of the data values typed in. As we can see, there should be 44 data values. The next column that I've named is called error, and this is what we're going to calculate from our original guesses. The next column is called meters for guesses and meter for error. So the cell right underneath the naming is an equation. So by giving things a name, whatever you choose to name them, if you hit equals, we can type in the name of the variable, which is the column name, and subtract 13. And by doing that, it will subtract 13 from all of the values from the cell next to it that's labeled guess. Likewise, if we wanted to rescale and go from meters to feet, we could take our guess amount and we can multiply that by 3.28. And again, we can see our guess to meters has changed. Same thing, we could do equals, and we can type error times 3.28, and we can see how far we are off in feet in comparison to the actual measurement of the room. And now, if you wanted to, we could have our 5-number summary for each one of these values. So just as a reminder, if you wanted to do the 5-number summary on the TI Inspire, we select the column that we want, go to statistics, stat calculation, one variable statistics, and I want 4 lists. So my first list is going to be guess. My second list is going to be error. My third list is going to be meter G. My fourth list is going to be meter error. And the resultants are going to be in column E. So we can see all of our summary statistics. Now I'm going to just spoil this just a little bit, and we're going to switch back to our notes. We can see the results of what we just calculated here. And you can see our guess versus our error versus feet, and then our feet and error. The measures of center move, and the measures of center are changed in each one of these, but the measures of spread, so standard deviation, are constant. And that's what we want to point out. Adding a constant only affects measures of position, like the mean and the median, but multiplying or scaling affects all of our measures. So going back to z-scores, standardizing data values into z-scores both shifts the data by subtracting the mean and then rescales the values by dividing their standard deviation. So we're doing a shift and a scale. Standardizing into z-scores does not change the shape of the distribution. So what is the z-score for the mean of a distribution? Well, standardizing into z-scores changes the center by making the mean 0, which is why we can compare everything once we shift and scale things to be centered at 0 and have a standard deviation of 1. So what is the z-score? 1 standard deviation above the mean? Well, if you could follow along, standardizing z-score changes the spread by making the standard deviation 1. And this is how we start to build our normal model. So just a couple more before we end this video. To find the mean of the z-score distribution, we have subtracted the mean from every score and divided by the standard deviation. Both transformations affect the mean. So the result is a mean distribution of 0. If you think about it, our z average would be x average minus x average over whatever standard deviation, which would be 0. So the standard deviation is only affected by multiplication. So the standard deviation of the z distribution is 1. So we have a mean with z-scores of 0 and a standard deviation of 1. A z-score then gives us an indication of how unusual a value is because it tells us how far away the raw score is from the mean. A data value that sits right at the mean has a z-score of 0. It's right in the middle. A z-score of 1 means the original data value is 1 standard deviation above the mean, versus a z-score of -1 means the original data value is 1 standard deviation below the mean. So when is unusual really unusual? And how far from 0 does a z-score have to be interesting or unusual? Because those are the things that kind of stand out. So there's no universal standard, but the more extreme a z-score, both negative or positive, the more unusual it is. We will have a more definitive answer soon. So just remember that a negative z-score tells us that the data value is below the mean, while a positive z-score tells us that the data value is above the mean. We are starting with z-scores to then build towards our normal model and our normal distribution with a mean of 0 and a standard deviation of 1. So first, we got to get good on calculating z-scores and being able to compare like with like when distributions are different, when means are different or standard deviations are different from two distributions. How do we compare those things? So that's what z-scores allow us to do. So we will move into the normal model in the second video, and then the third video will be actually doing some calculations. So we're going to stop here. We'll see you in part 2, Falcons.